Hello everyone, welcome to my YouTube channel. So guys, in this video, we are going to look at an interesting topic called bias variance trade-off. So it's a kind of problem in the machine learning field. So let us directly look at what is this bias variance trade-off. So in statistics and machine learning, the bias variance trade-off is the property of a model that the variance of the parameter estimated across samples can be reduced by increasing the bias in the estimated parameters. This is the basic definition. So you could wonder what this basically tried to tell us. So that means when we see a high bias, at the same time we can observe the low variance. And also when we look at the low bias, we could at the same time we could also see that there will be high variance. So it's okay. That's what if bias and variance, if you observe it, whether it is high or low, what could be the problem, right? So the thing is, so in machine learning, we'll try to build our model based on the training data set, right? So after we build the model, we'll test it on the testing data set or the validation data set, right? So if we're going to take that model to the production or the testing side, then this bias and variance term will affect the model, right? So that's why we look at this bias variance term, especially for the machine learning. So how does it going to affect? So generally, so after we build the model, if we try to evaluate on the test data set, there will be some error, right? So that some error, we can expect it as the expected test error, right? So then the expected test error will be equals to square of this bias plus variance plus noise. So basically what we need is a model which will try to minimize the test error, right? That means it should fit in a good way to the test, right? Whether it's in training or testing, it should fit in a perfect manner so that there will be low error, right? So in order to make it this expected test error low, let me draw it in tool. So we need to minimize this to low value, right? So if we want to minimize this value to low, then that means in the right hand side, we need to minimize all these terms to minimize, right? We need to minimize square of bias. That means we need to minimize the bias and we need to minimize the variance, right? And also you could think minimizing the noise. That's always not possible because the noise basically comes because of the data that we use to train or test. So basically that cannot easily reduce. We can reduce, but we cannot completely reduce that, or we cannot compensate that so much, right? So because we build our model based on the data set. So by choosing the right parameters and the right model, right? So using that, we can reduce the bias and variance using any other hyperparameter tuning, or as I said before, by choosing any perfect model for the perfect problem for this, right? So according to that, we need to minimize the bias and variance so that we could get low test error, right? So now you could get a good idea about the why you need to handle this bias and variance as low as possible and what is bias variance trade-off, right? So this is the basic idea, and you could understand well after watching this graph, right? In machine learning, you could see this graph so many times, right? So this is the graph, guys. So after watching this graph, you could understand well about the bias variance, right? So if we plot the error in the y-axis and algo complexity in the x-axis, right? So then if we have a model, right? If we have a model, we can choose any model, right? By increasing some algo complexity. If it's in machine learning, we can go get linear to non-linear models, right? And in deep learning, we can increase the high number of the layers, right? So that the algo will be or the model will be more complex, right? So if we take like that, and if we plot the model according to the algo complexity and error for the bias and variance and the total error, the graphs will be look like this. This white color line, right? That's for the scared of bias. Why do we take bias scared? Because the expected test error is not bias but bias scared. That's why we just take the bias and scared. So basically you can think it as bias, right? Not an issue, right? So when the algo complexity increases, that means you make it as non-linear model or increasing the more layers in neural network in the deep learning side, right? And that way, the error will become reduced, right? So if we increase the algo complexity, right, the error will be, the bias will be reduced, right? At the same time, the variance will be increasing, right? So, but what we need is addition of this squared of bias and variance to be low. So what we do is we just sum up, right? We just sum up this white and yellow color line, and that way you will get this red color line with addition of the noise, right? So because we also need to add noise, so noise will be same, right? So let me do that too in yeah. So if I take the noise as this, sorry about the drawing, it should be really horizontal or parallel to this x-axis. So assume this as parallel to this x-axis, right? So the noise will be fixed, right? So the noise will be fixed. The noise won't change for when we increase or decrease the algo complexity because the noise depends on the data set. So we are just changing the model, our model, right? But we don't change the data set. So choosing the data set is also a way to get a better model. After we fix the data set, we cannot touch the noise, right? So then we need to choose the algo complexity such that the square of the bias and the addition with the variance will be low. So for that, we'll add these 3 points, right? So we'll add variance, noise, and scared of bias. So like that we add so that we can get total error. So if we add like that, you can see we'll get the graph like this red one. So what we need is to the low total error, right? So that low total error, you can see that happens at this point. So if we want to have a good model, we have to choose our algo complexity at this point such that this error only we can expect, right? That means we can't completely reduce bias and also we can't completely reduce variance because at those points the error is so high, right? So the bias and the variance are comparatively low at this point. At that point, we need to choose our model, right? Now, I believe that you got a complete idea about this bias variance trade-off and how do we choose our model according to the bias and variance. So if you don't still understand this, don't worry guys, rewatch this video again or else just watch this. Just watch this picture, right? So if we take this axis as the bias, right? Bias increasing, right? This side bias is increasing. And this side, the variance is increasing. right? So you can see when there's a low bias and low variance, the data set will be look like this. That means when the variance got increasing, just compare this picture and this picture, right? When the variance got increasing, the spread will be high. And now look at this picture and this picture. When the bias increasing, it will move. That means the mean point will be moved, right? That's the bias and variance, right? I got this picture from this. So you can go and take a look at, right? If you don't believe me, okay. Yeah. So now we know that, okay, we need to reduce the error. So we need to take a intermediate value of the bias value and variance, right? But how can we increase the bias or decrease the and also the variance, right? How can we increase or decrease the bias and the variance, right? So if you want to increase the bias, what you have to do, you have to just make the model as non-linear model in machine learning, right? In machine learning. And in deep learning, you have to increase the number of the layers, such that you can increase the bias, right? And in some point, you got a model very complex and you have a high variance, right? So that what you can do is you can increase more data, because the variance means it's overfitting. That means it has low data and it fixed to that data. It performs well, right? It performs well to the training data set, and it does not work on the test data set. So you need to increase the more training data set such that it will be generalized the model, right? So for that, what you can do is basically you can add more data set, right? The size of the samples or the size of the data set, you can increase. Okay, you may say, okay, I cannot increase the data set, it's expensive or it's impossible to get more data, right? So for that, what you can do is increase the regularization, right? So in regularization means in deep learning, you can see the dropout, the famous regularization technique, right? And also in machine learning, L1, L2 regularization, right? So using the regularization technique also, you can decrease the variance. That means you are making the overfitting to the perfect fitting, right? So that means you are decreasing the complex of the model, right? So you can handle the bias and variance in this way. And I also forgot to mention that when there's a high bias, right? This point, high bias, that means that happens underfitting. Underfitting means, what does underfitting means? It does not perform on training data set and also testing data set, right? Because it does not perform well in training data set. That means it does not also perform well on test data set, right? That's obvious. So underfitting means it has high bias. That means it does not train well on the training data set, right? But overfitting is another case. That means it performed well on the training data set, but it does not perform well on the test data set. That means there are more error or more loss on the test data set. That is overfitting, right? So the thing is, in the overfitting, you may think you trained a model on a particular data set and it shows like 95% of accuracy, right? And you could think, wow, I got a good model, right? It performed 95% on training data set. But the thing is, if you tested the model on the test data set, that thing will reduce the accuracy, right? In overfitting. So generally if it gets a accuracy of 95% in the training, it should get at least 90 or 85 like that, if the model is a good model for the particular problem. But if it gets 60% or 70% like that, we are overfitted the model. We choose the overfitting model. We just overfitted the model to the training data, right? So for that, we need to reduce the complexity of the model, right? So that we can make it as perfect model or perfect fitting, right? Okay. And in summary, if you look at this table, you got overall or all the idea, right? So there are three cases: underfitting, just right, perfect fitting, and overfitting, right? I compare these three at the same time. So suppose in machine learning, you have under supervised, you have regression and classification, right? Yeah. So what is underfitting in regression? That means you have a data set like this, right? You have a model like this, a simple linear model. That means if it's in 2D, that means y is equal to mx plus c, that kind of model, right? This is the overfitting. It does not perform or it does not fit to the data very well. It's just a random prediction by just a human, right? Just join causing, that kind of model it works, right? And if you see the overfitting, it's overfitted. It passes through every points of the most of the points of the data set, right? It won't happen, or it won't be like that. So the just right is the nice model. You can see it's a perfect model. It just got low error. If you find error here, you can see this model has this from this data point you have this error, from this data point you have this error. If you go, and this point will have this much of error, right? This much of error will be high, right? And also you can see that okay, they have it's error will be low, right? You can see, oh, it's going to the all the points, so the error will be low. But the thing is, if you got a new data point at this point, right? Suppose I got a new data point at this point, right? The model will be show or get the value this, but the actual value will be like, for example, here, right? It's a huge difference in the test data set or test points, right? That's the regression in, that's underfitting and overfitting in regression. And also in classification also like that. See, there are two data points. In your left hand side, blue points are one category and the red points are another category. Yeah, it performs well, but the thing is, you could see like, okay, it's a good model, right? Some points are missing, but actually if you got more points, what will happen? There will be blue points like that, but it shows as red points, right? So those kind of issues are here, and you can see it's a perfect model, and you can see it's just overfitting. Like it try to pass through all the points, it try to miss all the points, right? If a new points come like this, right? Here a blue point, but what will happen? The model will predict as red point because it's in the red region now, right? So those are the issues here. But here, if you got the blue point, aha, it correctly performs, right? Okay. So that's in machine learning, and also in deep learning, you could see. So in the initial, the training and validation error will be high, right? So when you start to train for, that means you are increasing the epochs, not epochs, right? So when you increase the epochs, what will happen? Your training and validation error will be decreasing. So in underfitting, yeah, it's decreasing, but it stays at a higher points. It does not keep decreasing. That means we have also we can increase the epochs and we can reduce, but because of the layers also, if we increase the epochs also, it may won't decrease. At that kind of situation is this underfitting. But in just right, see, the training is become very low. Here the training error is very high, right? But here it's very low. If you take this 10% and it may be 50%, right? It's huge difference, huge difference, right? And also one thing you can know that, one thing you can know that is always or most of the time the validation error will be high. That's obvious, right? Okay. But in overfitting, what is happening is training error is really very low. That means nearly 2%. But for the testing, it's just really showing high value like 70%. Overfitted. Maybe because of the high number of epochs, right? Maybe we should stop this training at this point, right? Or else we have additional more number of layers, 10, 20, or high number of layers, right? So by visualizing also, you can understand what is overfitting and underfitting, and what you have to do is also mentioned here, the possible remedies, right? So in underfitting, you have to increase the complexity of the model and add more features because of the some features also it not perform well. So you can add more features also and train longer. See, you have stopped the epochs at some point. You can increase more epochs, right? Train longer is also coming. And in overfitting, because of the complexity of the model, you can get more data and generalize the model, or else you can perform regularization. As I mentioned before, in deep learning, you can perform dropout. And there are many things, batch normalization like that, and in machine learning L1 regularization and L2 regularization, and there are more regularization techniques. All right, guys. So these are the things that I would like to share with you guys. So I hope you got a good understanding, right, about this bias and variance trade-off and why do we need to handle that. So this is the overall picture, right? So we have looked at these these points, the underfitting and overfitting, and how those are related with bias and variance. So that's it, guys. So in another video, I will meet you with another interesting topic, right? And hope you guys are doing fine and keep enjoying and keep learning. And see you soon, guys. Yeah, and also I'm missing you, right? So we'll soon see you in the next video. Okay, guys. Bye.